Inductors and coils are a core electronics component and can be found in virtually every consumer electronic good and appliance. In a nutshell, inductors store electrical energy. They are built by wrapping a single wire and coiling it around a magnetic core. Now, coils like these are found in a myriad of electric components ranging from transformers, relays, solenoids, electromagnets, and even motors. All these coil-based electronics, including inductors, rely on electromagnetical relationships to function. Next, let's understand what inductors are, how they function, and what makes them so useful and unique. In a nutshell, inductors store energy in the form of magnetic fields. Now, these magnetic fields are created by current flow. Now, if you've watched my tutorial on capacitors, or you know how capacitors work, you might be asking yourself, don't capacitors also store electrical energy? And yes, capacitors store electrical energy in the form of electric fields, while inductors store electrical energy in the form of magnetic fields. So now let's talk about how an inductor behaves under a DC voltage. Let's make a flowchart and a DC demo circuit to understand how this works. Right now, the current across the inductor is 0 since the switch is open and there's no electricity flow in the circuit. As soon as we turn the circuit on by closing the switch, the current starts to flow in the circuit and the inductor. This change in current creates a magnetic field within the inductor, and this magnetic field takes some time to charge due to Lenz's and Faraday's law. Let's better understand Lenz's law before we continue. So just like physical bodies experience inertia, which is the resistance in change of their velocity, electromagnetic fields incur a similar phenomena where they create an opposing current in the direction of an EMF change. This is the exact same phenomena behind those viral videos where you see a small magnet falling very slowly through a metal pipe. This is where Lenz's law comes in. You can think of Lenz's law as electrical equivalent of physical inertia. So now we understand why the magnetic field takes some time to build and how, like inertia, it resists a change in current. However, once this magnetic field slowly starts to build, the inductor lets through more current due to a lower back EMF. You can think of the back EMF sort of like resistance. This lower back EMF now leads to a lower voltage drop across the inductor, making the inductor more and more conductive. Once this charging is fully done, the inductor acts like a conductor and passes electricity through normally. This process is called self-inductance. Do note that once you power off the circuit, the inductor will discharge its magnetic stored energy back into the circuit. This release in voltage is opposite in polarity to the original inductor's voltage, so you might need to take some precautions to protect your electronics against this release. Now let's move on to inductors and AC voltages. Inductors behave very differently under AC voltages. As you can see, AC voltages look something like this, which are basically a constant fluctuation of the polarity of the voltage. This constant polarity fluctuation means that the inductor doesn't have enough time to charge its magnetic field to the original AC voltage. And this is where a new term, reactance, comes in. Reactance is sort of similar to resistance in the sense that it lowers the current in your circuit. This reactance actually gets higher with higher frequency AC waves, because higher frequency waves have a shorter wavelength, which gives the inductor less time to charge. Because the inductor has less time to charge, it has a higher voltage drop the higher the frequency. Now, practically speaking, no inductor can be perfectly conductive, just like no wire or any sort of electronics is perfectly conductive in the real world. Now, when we combine this small internal resistance with the reactance of the inductor, we get something called the impedance of the inductor. Now that we have understood how inductors work, let's actually explore the different types of inductors and how we can use them. Firstly, this is the standard symbol for an inductor in a circuit diagram. Based on the type of inductor, the symbol can change slightly. Now, inductance is measured in a unit called the Henry, which is the rate of change of current and voltage. We can change the inductance of an inductor by tweaking several factors such as the length of the inductor, the number of turns in an inductor, the core material inside an inductor, and even the cross-sectional area of the wire used in the inductor. Finally, let's end this video by talking about some of the use cases of an inductor. Firstly, the inductor can be used as a filter. By combining it with a capacitor or a resistor, we can make a more specialized filter to filter out specific frequencies. Next, inductors and coils can be used as sensors. If you have seen the road near a traffic junction, you might have seen these black lines on the road. These are inductor coils that can actually measure the change in EMF and detect when a car is nearby. Next, coils can also be used in transformers, which use mutual inductance and not self-inductance to actually change voltages. And lastly, just like capacitors, inductors can be used for energy storage. And that's it for this tutorial. If you have any questions, you can leave them down in the comment section below. And if you want to subscribe for future tutorials like these, do feel free to do so. Thanks for watching.